So I outline here, so I will introduce my background of study and my data and analysis, then its result and discussion. So in this previous study, they combine very more catalogs from star cluster to galaxies and calculate their substance then progress. So this is stellar substance as a function of stellar mass. And let's propose this dashed line and let's say this is a statistical stellar substance. This line is a mass length about 3 multiplied 10 to the 5 stellar mass. And so, based on this line, they built a stellar evolution theory to explain why this line exists. So, in their theory, they calculate a critical density of stellar system, and with this critical density, they can conclude this spatial method. But there is some problem here. So if you consider about the galaxies, you can see this measurement line is not matched of the measurement density of galaxy, about 1 order. And another problem is this evolution theory is not fair to apply on all stellar systems from star cluster to galaxies, because the mechanism of their formation may be different. And another problem is if you apply the galaxies measurement to their evolution theory, you can see it's not matched. They propose this gray area, but for galaxies this orange area. So I want to check this measurement of gas, density measurement of galaxies in this work. So my data is from SDS SDR12, and I take the photometric and estimation of stellar mass and emission line. So for these galaxies, I select for redshift smaller than 0.05 to 0.5. This is from K correlation limit, but it's also for local galaxies. And this is magnitude limit and stellar mass error limit. I will explain on next slide, and for reliable photometric. And so eventually I get about 400,000 galaxies. This is a large sample in comparison with their catalog, because in this plot they only combine about 10,000 of galaxies, and this another thing is this galaxy redshift is from 0 to 4, so it's a wide range of redshift. And for some galaxies, their stellar mass error is weak. It's smaller than 3 sigma of the median. And we check these strange gases, and from the color of them and strong of typical emission line. So this could lead expectation of SED peaking, and that the stellar mass emission is failed. So I drop this 4,000 gases about 1%. And for analysis, I think that the stellar substance represented is a big sigma, is stellar mass divided by pi multiply ratio square. And high sigma galaxy is the galaxy with sigma larger than 2 standard deviation above median. So I choose the C model for galaxy to check to select the ratios of galaxies. The stellar mass range of galaxy is 10 to 9 to 10 to 12 stellar mass, some mass, and I divided this to each mass being 4.1 log mass and calculate the median and sigma of each mass being the gray line and the orange point. And finally, I fit this orange point to 1 sigma mass line, it's 2 sigma line, the black line, and for galaxies above this red line, I call them high sigma galaxies. So there are about 8,000 galaxies. For my result, you can see there is a increase in stellar mass density. So the maximum of this density is not a constant. Instead of mass dependence, you can see the maximum of density is increased when mass is increased. And another is these high sigma galaxies, all of them are red and low star formation rate.
It looks like you picked out the bulges of galaxies.
Yes.
They're red. They're in that mass range. They're the most compact. They're the highest surface brightness objects that we know of in galaxies. As you get to more massive galaxies, there's a strong relation that the surface brightness goes down.
So for these galaxies are red, so we think there's a consequence of evolution because high density galaxies are evolved, and to explain this mass dependence of stellar substance, we think about the balance. So for less massive galaxies, the feedback of star formation of supernova or mechanism trunk, so gas goes away by this feedback, so star formation rate is low or no star formation. So they can't reach the higher density, and for higher mass galaxies, the potential of galaxies strong, so the gas is go back, yes, it come back, and star formation is still going, then they can reach higher density. And so this is our result, and you can see in this mass range, the density measurement is decreased, but for mass above 10 to 11, this line becomes flattened or turned down. So we want to explain this. This may be a result of density evolution from high pressure. So there are some observations that massive and passive gases in high V above V equals 4 universe. And if you apply some evolution scenario to these highly galaxies, in either major merger or minor merger, the density could be go down because the size is increasing. So if you apply the major merger, galaxy in redshift equal 4 will be there, and it will go down. If you apply minor merger, it will be here. You can see the major merger case, the galaxy is over the maximum line proposed in previous study, and if you apply the minor merger, it just in the maximum line. So the first step of this study is because I just use the local galaxies and in SDSS, so you can extend the mass range to lower mass of gases and high ratio gases to check if this mass dependency continues. And another thing is one can revise the evolution theory due to this mass dependency relation. So I think my summary is here. Thank you.
So, any questions, comments? Start first.
Not my field, but so interesting question. How do the galaxies get to have such a high surface density? Although the nuclear star clusters are much denser, by a factor of 10. But anyway, I mean, these galaxies might even have a nuclear star cluster. I guess you have to have a space telescope to see it. But anyway, I thought that people said to get the rather high stellar density in a bulge, you must have a lot of dissipation, and that really means gas. So I don't know if it makes it, I don't care if it's a major or minor merger, but I think it has to be a wet merger. You know, wet, it has a lot of gas in it, because that can get into very small region, a lot of mass. But I'm sorry, I just don't know. This is an extensive theory about bulges of galaxies, how they form, and so on. So I'm sorry, I don't really know what the latest literature is, but I think it might be relevant to your work, maybe.
So, further questions, comments? So if I can have one. So maybe I have missed the first part. So you included all the galaxies from this one, or you didn't select just the morphological type galaxies, or?
Yes.
So you used all the galaxies. Right?
Yes. Yes.
So probably in the plot is a mix of probably spiral galaxies and the other type galaxies, right?
Yes. We check the morphological of these gases, and we don't find any difference.
Any difference?
And
If you go back to this plot that you showed, yeah, this one, for example, anything. Yes. Probably if you plot a spiral galaxies and a other type galaxy separately, probably they will populate differently, right? So probably this part, the other type galaxies will dominate, and probably the other type galaxies will be there. So
yes.
you are looking at two different types of galaxies.
Yes, maybe.
Probably the related question is, I wonder why, for example, the surface mass stellar density start to decrease after 10 to 11, let's say, the stellar mass. Do you have any good idea why it starts to decrease?
We
Okay, so we suppose that our size evolution of massive galaxies. So actually in the local universe we found very dense, high dense massive galaxy. And that's the region. Then according to the size evolution, if you go back to the high Z, the size must be smaller than local universe because of the evolution. So if you go back to the high Z, assuming this minor channel, for example, we can expect the original size of this galaxy by assuming the model.
Okay.
Then
It's
also
very high.
very high should be
Very
high.
high.
The starting, we don't know where the starting model, but should be very high compared with the local universe. And also combined with say this is just a discussion. We combined with downsizing formation of galaxies. More massive galaxies should form earlier than less massive galaxies. That means massive galaxies had a more time evolution, size evolution, compared with less massive galaxies. Then if they have a lot of time to evolve size evolution, this guy must be more smaller, lower density compared with less massive. That is one possibility, but I'm not sure.
Very interesting.
Yeah.
Okay, other questions or comments? Okay, if not, let's thank you again.